All right, let's jump straight into this explainer and look at how chemists manage to decode the completely invisible structures of molecules using nuclear magnetic resonance, or, NMR. It's honestly a fascinating technique because it lets us take a chemical sample and deduce exactly how its atoms are wired together without ever needing a microscope. Today, we're going to zero in on how hydrogen atoms, or protons, interact with one another, and how we can literally read those interactions like a map.
So, here's our quick roadmap for today. First, we'll look at the molecular neighborhood, then the N+1 rule, the origins of splitting, Pascal's triangle, and finally, measuring coupling constants.
All right, part one, the molecular neighborhood. We're looking at protons as neighbors.
Now, you might be wondering, how exactly do you map a neighborhood you can't even see? Well, we map it by observing how the inhabitants, the protons themselves, talk to and essentially sense their next-door neighbors on adjacent carbon atoms. In NMR spectroscopy, these protons act like tiny little magnets. When you put them in the massive magnetic field of an NMR machine, these magnets will either align with the field or against it. But the kicker is, they aren't isolated. They can actually feel what the proton on the very next carbon atom is doing.
And that brings us to a really core concept called spin-spin splitting. This is literally the chemical readout of these molecular neighbors interacting with each other. When a proton senses the spin of its neighbors, the single clean signal, or peak, that we'd normally expect to see on an NMR graph actually gets split up into multiple distinct components. It's kind of like the neighbor is whispering to the proton, altering its energy state just a tiny, tiny bit, which our machine then detects.
Right, moving on to part two, the N+1 rule and how we actually predict that split.
So what's really cool about this interaction is that it follows a super predictable, simple empirical rule. Using what we call the N+1 rule, we can see how a solitary next-door neighbor splits the signal into two peaks. We call that a doublet. If there are three equivalent neighbors, like say a methyl group next door, well, that N=3 creates a quartet, or four peaks. To give you an example, in a molecule of ethyl iodide, the three protons on the methyl group sense the two protons on the adjacent carbon, splitting their signal into a triplet. It's incredibly consistent. It acts basically like a direct head count of who lives next door.
Let's get into part three, origins of splitting, or the quantum why behind all this.
The crucial point here is understanding why these neighbors cause this splitting in the first place. At the quantum level, a hydrogen on carbon A, let's call it H sub A, senses the magnetic spin direction of the hydrogen on the adjacent carbon B. Remember, proton B can be spinning in one of two ways. It can be aligned with the magnetic field, which is a lower energy state of +1/2, or opposed to the field, which is a higher energy state of -1/2. So, in any given solution, about half the molecules are going to be the X-type, where proton B is aligned, and the other half will be the Y-type, where proton B is opposed. Proton A physically feels this difference, so its signal gets split into two distinct absorptions of exactly equal intensity.
Now, it gets even more fascinating when we start adding more neighbors. Think about the possible spin arrangements of methyl protons causing a triplet. Because molecules have different combinations of these spin arrangements, like those up and down spin combinations, they create multiple distinct energy states. If you have two neighbors, both could be spinning up, both could be spinning down, or, and this is the absolute key, one could be up while the other is down. Because there are two different ways to arrive at that mixed up-down state, that middle energy arrangement is literally twice as likely to occur in your sample. And that probability, it directly dictates the intensity, or the height, of the split peaks we end up seeing on the readout.
All right, part four, Pascal's triangle, the elegance of ratios. So check this out. The intensity ratios of these split peaks, like that 1:2:1 ratio of the triplet we just talked about, perfectly follow the entries in Pascal's triangle. It's amazing. Each entry in this famous mathematical triangle is just the sum of the two entries directly above it. A doublet is 1:1. A triplet is 1:2:1. A quartet is 1:3 to 3:1, and so on. It is a stunning example of quantum mechanics perfectly mirroring classical mathematical probability.
By just memorizing these standard splitting patterns and their corresponding Pascal intensity ratios, a chemist can immediately identify exactly how many adjacent neighbors a specific proton has. You just look at the graph, you see a signal split into a neat 1:3 to 3:1 quartet, and you instantly know, okay, this proton lives right next door to exactly three other equivalent protons. It's essentially an infallible molecular decoder ring.
Which brings us to part 5, measuring coupling constants, the invariant ruler.
Now that we actually know how many peaks there are and how tall they are relative to each other, we need to pay attention to the space between them. If you look closely, the distance between the individual peaks within a multiplet, which we represent with the letter J, is completely constant across the entire group. This distance is called the coupling constant. It's a precise measure of exactly how strongly a nucleus is affected by the spin states of its neighbor, and it's measured in Hertz. If two different groups of protons are splitting each other, that distance J will be perfectly identical in both of their respective multiplets.
And here's what is truly amazing to me. This coupling constant is a true invariant. Whether you're using an older 60 MHz spectrometer or a highly advanced 100 MHz spectrometer, the J value in Hertz absolutely does not change. While the overall chemical shifts might spread out further on a much more powerful machine, the spacing between the split peaks of the multiplet is totally locked in by the physical bonds of the molecule itself. For instance, going back to ethyl iodide, that coupling constant is exactly 7.5 Hertz, no matter what machine you use to look at it.
Now, one quick caveat. Keep in mind that this neat N+1 rule perfectly applies only in what we call first-order systems. This is where the chemical shift difference between the interacting groups of protons, which we refer to as delta nu, is significantly larger than the coupling constant J that links them together. As a rule of thumb, we usually want that ratio to be greater than about 6.5. Because if the peaks get too close together on the chart, the system becomes strongly coupled. Then those nice, clean Pascal's triangle patterns start to distort into much more complex second-order spectra, which, honestly, is a massive headache for another day.
So, as we wrap up this explainer, I really want to leave you with this thought. If we can decode the invisible language of atomic neighbors using such simple math, how might mapping these hidden interactions accelerate the discovery of tomorrow's life-saving drugs or revolutionary materials? We've gone from unseen spinning protons to predictable mathematical patterns, to invariant constants that tell us exactly how atoms are linked. By mastering these invisible neighborhood maps, we aren't just looking at chemicals, we're literally reading the blueprints of nature itself. Thanks for joining me on this deep dive into spin-spin splitting, and keep questioning what you can't see.